Hello Year 13. I'm doing this video because one of the questions that I marked in the electricity paper from last week showed a few misconceptions. So I'm just going to look at VI characteristics. Now there's three things you need to know the VI characteristics for: a bulb, an ohmic conductor or a resistor, and a diode. And I think you'll all remember the shapes of the graph. The bulb is the one that looks like that, or it could be a filament lamp. Ohmic resistor is a straight line showing directly proportional, and the diode is the one that goes along. It doesn't go up here, it goes along to there, and then it goes up like that. Now with these graphs, remember what's on the x and the y-axis. It's always potential difference on the x-axis, current on the y-axis, because when we're doing these, you are changing the potential difference and seeing what happens to the current. Okay, so IV characteristics. First thing is make sure that you know the circuit that's used. Slightly different to the GCSE one because you'll have your power supply, and it will normally be a fixed power supply, and you use one of these circuits where you use your rheostat and you put whatever the component is. I'll just write component there. So whether that's the bulb, the resistor or the diode, you get an ammeter in there to measure the current, and you'll put a voltmeter over the component. Now the reason why you do this and don't just stick a variable resistor in the circuit is because this way you get a full range of the potential difference. So if this was 6 volts, you could slide this along here and get 6 volts over your component, or you could slide it along here and get 0 volts over your component. If you just stick a variable resistor in the circuit, you can't get that full range. Okay, so then we're looking at these graphs. Quite often you've got to say what's happening to the resistance. You know, or you should know, that what resistance is, our definition, is its potential difference divided by current. Okay, so what the misconception was a lot of you were saying, well, that's the 1 over the gradient, but it's not. What you've got to be able to do to find the resistance, if you want to find the resistance when V was 3 volts, you read this point here, whatever this current is, say the current was 1 amp at that stage, you do 3 divided by 1. That's different to what the gradient would be at that point, or the inverse of the gradient would be at that point. The gradient doesn't show you the resistance. It is just using this equation here that shows you the resistance. Now, if you look at the ohmic resistor, I suppose you could say it's the inverse of the gradient, but that only works because it's a straight line. So if you had a steeper line, you could see straight away that a steeper line will be a lower resistance and vice versa. But if we're looking at the bulb or indeed the diode, you've just got to read point by point what the resistance is. Now, if you think about what the resistance would be at these points, what you'd have is the resistance getting bigger, okay? And you need to know why the resistance gets bigger, and that's because as the current gets bigger, it heats up, and for most things, temperature and resistance are sort of, proportional. You get a higher temperature, you get a higher resistance. That doesn't hold for a thermistor. Thermistors are the other way around, okay? Now, in the question you had to comment on the resistance of the diode. Now here, when we've got a negative potential difference, here, a lot of you were saying, well, the resistance is 0. It's not, is it? The resistance of the diode, when we've got a horizontal line like that, it is infinite. And it stays infinite to this bit here, okay? Then what happens is, if you have a look at there, we've got a very small current. So when we're going resistance is V over I. We've got a very small current, so we've still got a high resistance. When we're looking at this bit here, V over I, you've got a much bigger current, so what would happen is that resistance would decrease. So you've got an infinite resistance decreasing, okay? So make sure that you are aware of that. Now, when you're looking at resistance, there is a page on the book that looks at the effect of temperature on resistance, and it talks about, it's page 175 in the book. it talks about the resistivity, because it's not just resistance that changes, it's resistivity that changes. And the resistivity at a particular temperature is equal to the resistivity at a known temperature. And then we've got this equation here, 1 plus, we've got alpha, which is the temperature coefficient, and then we've got T minus T0. Okay, so what that is that's the resistivity at a known temperature. That's the resistivity at a different temperature. That's the temperature coefficient. Most things have got a positive temperature coefficient, and if you think about what that means the higher the temperature, the higher the resistivity. Thermistors are sometimes called negative temperature coefficient thermistors, and that's because this bit here would become negative, and what that would mean is at a higher temperature the resistance drops. So if we looked at resistance against temperature for a thermistor, it goes like that. Okay, if we looked at resistance against temperature for any sort of conductor, it goes like that, if that was an absolute scale. So you've got that graph you need to know, but be aware that thermistors are special and most things don't do that.